Today, we are going to demonstrate the Franck-Hertz experiment, the schematic diagram.
This is argon-filled tetrode. The tetrode consists of cathode, grid 1, grid 2, and anode. A filament is used to heat up the cathode so that it can emit electrons. Two cascaded current amplifier is used to amplify the anode current. Here, AD620 op-amp is used to amplify the current in both cases. To see the variation of the anode current by DSO, a current to voltage converter is needed. Here, a 741 op-amp with the required circuit arrangement converts the current to voltage, and we can observe the current variation through the similar voltage variation by the DSO. For this experiment, a platform is specially designed with a socket of the tetrode to smoothly connect the pins of the tetrode as shown in the picture. In the picture, you can see the tetrode is connected with its platform. Different pins of the tetrode are connected with the button of the platform. This is cathode, this is grid 1, this is grid 2, these two are filament points, and this is anode point.
Now, we are going to demonstrate the Franck-Hertz experiment with argon tetrode. This is argon tetrode. These two pins are filament pins. This is connected with this power supply. Approximately 4 volt is given to the filament pins. So these two filament pins with 4 volt heat up the cathode, and the cathode emits thermoelectrons. Now the cathode and the grid 1 pins are connected. Basically, the cathode pin is connected with this negative of this grid 1 power supply, and the positive of the grid 1 power supply is connected via this galvanometer. This is worked as a microammeter, and this microammeter is connected with this grid 1 pin. So, a positive voltage is given to the grid 1 point by this grid 1 power supply. Thus, the cathode is in negative potential and the grid 1 is in positive potential with respect to the cathode. So, thermoelectrons are accelerated due to positive potential of the grid 1, and they rushes towards the grid 2. Some parts of the electrons also collected by the grid 1 and constitutes the grid 1 current, which can be observed through the microammeter. Now for grid 2 connection, this is cathode point, this is grid 2 point, and the grid 2 is connected with this with series with this microammeter. So grid 2 is connected in series with this 200 microammeter, and the other point the other point of this microammeter is connected with this positive terminal of this we can say it is a power supply, and the ground point of this power supply is connected with this cathode point. So, in this diagram, this is grid 2 power supply, and the positive terminal of this grid 2 power supply is connected with the grid 2 point, and also in series a 200 microammeter is connected, and the ground point of this power supply is connected with the cathode. The potential of the grid 2 point should be much higher than the potential of the grid 1 point, so that the accelerated thermoelectrons can reach the grid 2 point and onwards. Now, this is the arrangement for high voltage output power supply for the grid 2 point. As we don't have any programmable power supply which can give 90 volt output, so we have used PA85 op amp as a voltage amplifier. Using this op amp, we can supply almost 90 volt in a specified interval to the grid 2 point. The circuit arrangement is shown in the picture. Here, this 0 to 30 volt programmable power supply is connected with this PC. We can regulate the power supply using Python and SCPI coding, so that the output of the power supply can be changed accordingly. The output of the power supply is further amplified and fed into the grid 2 point. Now this is Python and SCPI program for 0 to 30 volt power supply, and this is PA85 op amp voltage amplification circuit. Input 0 to 30 volt, output is 0 to 90 volt. The input voltage coming from the 0 to 30 volt programmable power supply is changed in a suitable manner using Python and SCPI command, so that the output voltage changes accordingly. This is the voltage amplifier circuit for PA85 op amp. These three are biasing arrangement for this PA85 op amp. This is, you can see, this is PA85 op amp, which is biased by this power supplies, which are plus, the biasing is plus 120 volt and minus 60 volt. Now, this is a 0 to 30 volt programmable power supply, which is the input of the PA85 op amp. The positive and negative terminals of this power supplies, these are the positive and negative terminals of this power supply, which is the input of the PA85 op amp. This programmable power supply is programmed with Python and SCPI program. This is the PC, which is the laptop. You can see the program. This Python and SCPI program is so programmed that the input of this power supply is vary in the interval of 1 millivolt or greater than 1 millivolt. This power supply is connected with this PC via this USB connection. So this is the positive terminal of the 0 to 30 volt power supply, and this is the negative terminal of this power supply, which is connected with the voltage amplifier PA85 op amp. Now the amplified output is connected with this grid 2 and cathode point via this 200 microampere uh, ammeter, DC ammeter, which shows the grid 2 current. Now once again, this is argon filled tetrode, this is anode, and this is the power supply for the anode, and the power supply is connected with the anode. The negative terminal of this power supply is connected with the anode, so that we can see or observe the Franck-Hertz effect in the anode current. So this is anode source, this is the positive terminal. Terminal of this anode source is connected with grid 2, and the negative terminal is connected with the anode point. Now as the anode current is of few nanoampere, so we have used two cascaded current amplifier using AD620 op amp to amplify this nanoampere current to microampere current. Now this is anode supply. As you see, this is anode supply. The positive of this anode supply is connected, positive of this anode supply is connected to the grid 2 point, and a negative is to be connected with the anode. Negative of this supply is connected to the anode. But before the anode connection, we have connected the negative end to the current amplifier, and the other end is connected to the anode point, So this is the amplifier input, which amplify the nanoampere current to the microampere current. This is the input of this 8620. Here you can see this is the circuit arrangement for the 8620 amplifier. So here is the circuit arrangement for current amplifier using 8620. The input current, which is anode current, it is in nanoampere, and after amplification it becomes microampere. So 1000 times amplified. Now we have used another 8620, and this time another 1000 time amplification, and the microampere current goes to milliampere current. So this is nanoampere input current, and this is microampere output current by 8620, and this output current is fed into this second stage 8620. This is power supply, which is the biasing arrangement for this first stage 8620. This is input current, this is output current, and this is fed to this uh, second stage 8620. So once again, this is second stage 8620. This is the output of the first stage 8620. This is output of the second stage 8620, and this is connected in series with this milliammeter. This is the biasing arrangement for the second stage 8620. So these two are output of the second stage amplifier, and this is connected in series with this milliammeter, and one wire is connected to the ground point and another is connected to the second pin of this current to voltage converter. This is a current to voltage converter. This is 741 op amp, and the diagram of the current to voltage converter is shown in this picture. So this is the these two are output of the current to voltage converter. This is connected with this coaxial cable and uh, and fed into the this DSO to see the voltage variation of the anode current. Once again, this is Python and SCPI program to regulate this 0 to 30 volt power source, and this is P85 voltage amplifier, filament source. This is anode source, negative 5.3 volt is given, and grid 1 source 1.9 volt is given. These two are current amplifier, this is ammeter, and thus we can see the anode current variation in terms of voltage variation through this DSO. The current to voltage converter converts current variation into voltage variation. You can see the voltage variation using this DSO. After some slight enhancement of the DSO parameters, we can see clearly the voltage variation, which is similar the anode current variation, and hence the Franck-Hertz effect, or we can say the experimental result of the Franck-Hertz experiment. Now once again, this is 0 to 30 volt power source. This is PA 85 voltage amplifier. You can see the grid 2 current, filament voltage, grid 1 current, anode and grid 2 power source. 6.3 voltage is given to the anode point, and now this is the current variation of the anode point. And now you can see the voltage variation and the current variation of the anode point simultaneously.